Every moment, the ground beneath Iceland is slowly drifting, shifting by just a few centimeters at a time. This nearly invisible motion has shaped one of the most volcanically intense regions on Earth. More than 130 active volcanic systems have emerged, stretching open fissures for kilometers and unleashing lava hotter than 1,100 degrees Celsius. In just a matter of hours, that heat is capable of burying and erasing an entire town. Against a force like this, humans have no way to shut down an active volcano. Once an eruption begins, it cannot be turned off. The only option available is resistance through delay, constructing barriers designed to slow lava's advance rather than stop it outright. In today's video, Mandarin Tech explores a critical question. Can people truly control lava, or are we simply gaining a little time before nature takes over? Although it is known as the land of ice, Iceland ranks among the most geologically active places on the planet. The country sits directly atop the boundary where two enormous tectonic plates are slowly pulling away from one another. As they separate, molten rock from deep inside the Earth rises upward, fueling frequent volcanic eruptions. In most cases, lava spreads across empty stretches of hardened black rock, far from human settlements. But when a flow changes direction and moves toward towns or infrastructure, it instantly becomes a serious danger. Iceland experiences an average of 4 volcanic eruptions every year, yet no one can reliably predict where the next one will break through the surface. When an eruption that began in 2023 spread across roughly 15 square kilometers, Icelandic authorities reacted without delay. A massive emergency effort was launched, centered on building lava barriers, enormous earth walls constructed for one purpose only: to slow the advancing molten rock. These lava barriers are not fully planned or finalized structures from the start. Instead, they evolve continuously as conditions change. Just beyond one of these rising walls stands a geothermal power plant, a critical facility that delivers heat and electricity to a large portion of the country. If lava were to reach this site, the impact would go far beyond a single location, potentially disrupting daily life for tens of thousands of people. At the height of the operation, the barrier grew to nearly 20 meters tall. Over a period of 6 months, engineers and crews relocated more than 3 million cubic meters of material, mostly volcanic rock mixed with soil, to shape the growing barrier. Despite this enormous effort, the lava did not simply halt. At several points, molten rock spilled over the top of the wall. When this happened, emergency crews had no choice but to spray water directly onto the glowing surface. The rapid cooling helped slow the lava's movement, buying precious time to strengthen and extend the barrier. From an engineering perspective, lava barriers are far simpler than concrete dams or water control structures. At their core, they are massive earthen embankments built gradually, with each layer adding roughly 1 meter in height. What makes them effective is not complexity, but an understanding of lava's behavior. Unlike water, lava does not soak through soil. Its extreme heat and thick, viscous nature cause it to move across the ground, guided mainly by gravity, slope, and terrain. Because of this, engineers can focus on height rather than deep foundations. If the wall is tall enough to slow the flow and redirect it away from critical areas, it has done its job. When conditions demand it, the barrier is raised again, 1 meter at a time, until the lava either cools, stalls, or finds a different route. To build at that pace, Iceland assembled a massive earth-moving fleet rarely seen concentrated at a single site. Machines such as the Komatsu 375, Liebherr 776, and Caterpillar D11 worked alongside long lines of articulated dump trucks. This display of heavy equipment was not about scale or spectacle. It reflected a simple and urgent truth: with every passing hour, the lava continued to move forward. Only by transporting material at maximum speed could the barrier hope to stay ahead of the advancing molten rock. Construction begins directly on top of lava that has already cooled and hardened from earlier eruptions. Over time, this material turns into dense basalt, a rock so tough that breaking it apart is a challenge on its own. Bulldozers fitted with powerful ripper teeth tear into the basalt, focusing their immense weight onto narrow contact points to fracture the surface. Once broken into manageable pieces, the rock is pushed into large stockpiles. Excavators then load it into trucks, which run non-stop between the excavation zone and the barrier itself. At the construction site, the reclaimed lava is dumped, spread, and compacted carefully, layer by layer. Each additional meter of height is calculated in advance, turning what was once destructive molten rock into the very material used to slow the next flow. At this location, material that once destroyed roads and buildings is repurposed as the core of the defensive wall itself, forcing new lava flows to slow, spread, and change course. Lava has no awareness or intent. It does not plan or target. Driven only by gravity, it follows the lowest path available, overrunning everything along the way, including highways, power networks, and entire neighborhoods. Once molten rock passes through an area, many places can no longer be reclaimed and must be abandoned altogether. Faced with this reality, the people of Iceland respond not with panic or the illusion of total control, but with acceptance and adaptation. At times, the intense heat of lava flows is even used to cook food. This is not an act of recklessness, but a quiet reflection of everyday life in a country where volcanic activity is a constant presence. It represents the composure of a society that understands the limits of technology and chooses to protect what matters most within the narrow window of time that lava barriers can provide. But that time is not always available. When lava is only a few dozen hours away from vital infrastructure, constructing large earthen walls becomes nearly impossible. This limitation was clearly revealed during the Reykjanes eruption in 2024. Lava not only overtopped existing barriers through newly opened fissures, but also broke through sections built over paved roads. The smooth surfaces offered less resistance, allowing the molten rock to push forward more easily than anticipated. In moments like these, humans have occasionally turned to far more extreme solutions. In Hawaii, during eruptions in 1935 and 1942, military aircraft dropped bombs weighing roughly 600 pounds into lava tubes on Mauna Loa. The goal was never to stop the volcano itself, but to disrupt the internal channels feeding the flow, forcing lava to spill out near the blast sites instead of continuing downhill toward populated areas. The results were inconsistent. In some cases, the lava slowed briefly. In others, the explosions had little to no measurable effect. Still, when options were limited and time was running out, intervention, even with uncertainty and risk, was seen as a better choice than standing by and watching the lava advance unchecked. History shows that in certain situations, humans have managed to interfere with lava flows using surprisingly simple techniques. One of the most well-known examples comes from Iceland's 1973 Eldfell eruption. As lava advanced toward the town's harbor, engineers pumped seawater directly onto the molten rock. The sudden cooling caused the lava's surface to harden and slowly solidify. This hardened crust acted as a temporary natural wall, forcing the lava behind it to slow down and shift its direction. While this approach could never stop a volcano itself, it demonstrated that under specific conditions, lava can be cooled and redirected long enough to shield critical infrastructure and gain valuable time. In reality, nearly every attempt to control lava, whether through explosives, water cooling, or massive earthen barriers, has the same objective: buying time. And when that time is sufficient, communities do more than rebuild what was lost. They learn to transform the land that was once devastated. Volcanic slopes, typically found between 400 and 800 meters above sea level, offer unique natural advantages. Soil created from cooled lava is exceptionally rich in minerals such as potassium, magnesium, and iron, all of which are essential for healthy grapevine growth. The porous nature of volcanic rock allows rainwater to drain quickly, forcing vine roots to grow deeper in search of moisture. This process produces stronger, more resilient plants. Most vineyards in volcanic regions are planted facing southwest. During daylight hours, they receive enough sunlight to support photosynthesis without overheating. At night, cooler temperatures slow the ripening process, allowing sugars and complex flavors to develop in balance. Over time, hillsides that were once lifeless black rock become covered with thriving vineyards. Each year, growers harvest thousands of tons of high-quality grapes from land once considered unusable. When new vines are planted, each one is placed into a hole about 40 centimeters deep. The soil is carefully blended with organic compost and volcanic ash, helping young roots anchor quickly while absorbing minerals left behind by past eruptions. The dry, windy conditions common in volcanic regions further benefit grape cultivation by reducing excess moisture. These conditions are ideal for producing thin-skinned grape varieties. The thinner skin allows grapes to absorb sunlight efficiently while minimizing moisture retention, a key factor in preventing disease and maintaining grape quality. After roughly 3 years of careful tending, the vines begin to produce their first usable harvest. Grape picking usually starts early in the morning, while temperatures are still low and a thin layer of mist rests on the clusters. Harvesting at this time helps preserve natural moisture and limits oxidation before the grapes are transported to the winery. Each season, tons of ripe grapes are gathered from slopes dusted with volcanic ash. Depending on weather conditions and the specific year, a single hectare of vineyard can produce between 8 and 12 tons of fruit, an impressive yield for terrain once thought to be unfit for agriculture. Once harvested, the best grape clusters are delivered to the winery on the same day to maintain freshness and retain natural sugar levels. There, the grapes are carefully washed to remove ash, dust, and remaining debris. They are then destemmed and sent into sealed pressing systems. The pressing process is closely controlled to extract clean juice while limiting the release of compounds that could cause bitterness or excessive astringency. The extracted juice is transferred into fermentation tanks, where natural yeast converts sugars into alcohol while developing flavors unique to volcanic terroir. After fermentation is complete, the wine is aged for several months in oak barrels. This aging phase helps stabilize the wine structure and deepen its complexity. Once the desired balance and maturity are achieved, the wine is bottled and stored in cool cellars for further aging. What emerges is a finished product born from land that was once buried beneath molten rock. At first glance, lava is synonymous with destruction. It consumes roads, engulfs homes, and forces communities to abandon land that has supported generations of life. But when viewed across the long history of human interaction with volcanic forces, lava's role extends beyond devastation alone. It becomes a reminder of the limits of technology and of how people choose to respond, adapt, and ultimately reshape their relationship with nature. In efforts to build barriers and redirect flows, lava remains a force that cannot be defeated, only slowed. Earthen walls, rock embankments, and man-made barriers are never built with the expectation of defeating a volcano. Their purpose is far simpler and far more realistic: to gain time. This reflects a fundamental truth. Technology can guide and redirect natural forces, but it cannot command them. When time runs out, humans have occasionally turned to extreme actions, including bombing lava tubes. These dangerous and uncertain efforts reveal how far people are willing to go when facing forces that lie beyond direct control. Yet the deepest significance of lava appears only after it cools. Landscapes once burned and buried slowly transform into mineral-rich terrain where grapevines can take hold and flourish. What began as destruction becomes the groundwork for renewal. In this transformation, humans stop fighting lava and instead learn how to work with it, shaping their lives around its presence. From the same hardened basalt, geothermal water filters upward, forming ecosystems like Iceland's Blue Lagoon. This unique environment is both naturally restorative and a defining economic and ecological symbol of the nation. From defensive barriers and explosive interventions to fertile vineyards, lava reveals a consistent principle. Humanity does not overcome nature through raw force, but through adaptation, patience, and the ability to turn danger into opportunity. Lava barriers do not stop volcanic eruptions. They simply extend the window of time available. In Iceland, earthen walls are built not with the illusion of total control, but with the goal of protecting what can still be saved: infrastructure, energy systems, and human lives. In this struggle, there are no perfect answers. There are only rapid decisions made under pressure, where every choice carries consequences. When lava cools, life does not return to its previous state. It returns transformed, more cautious, more aware of its limits, and better suited to the land it occupies. After every eruption, what remains is not only stone, but knowledge, lessons shaped by experience, and a deeper understanding of how humans coexist with the power of nature. So the question remains, what are the true limits of humanity when faced with Earth's immense geological forces?